Okay, so let's start today's lecture. And one more thing that I should mention regarding the last lecture, I noticed that the last lecture when I recorded, only my voice has been recorded and I couldn't see my screen. So what I can do for partitioning part, I can send you or post you my notes for the partitioning part, and of course I can post my voice which is recorded, so you can use like the voice, the audio, and notes that I will post on Sakai to review what we learned in partitioning and the reduction the circuits. But today I try to make sure that everything is recording. So far, I'm trying to record it with two different software, and I hope that at least one of them is doing its job properly and recording what we talk today. Any question? Okay, so the next thing I'm going to tell you is regarding your exam 2. I just graded half of the exam and I'm still grading the exams. I will post your grades by the end of this week, and I also will post the solutions online so you can compare your solutions with what is the correct solution. Uh, so by this weekend, you will receive a notification, Sakai notification, that your grades for exam 2 has been posted, and you can go on Sakai and check your grade. Okay, and the next thing is hold on a second. Okay, so any question? Uh, if you have any question for the exam, let's discuss it next week because first let's have your grades and then we can discuss about the problems on the exam. Okay, today we are going to learn something new. So far, in synchronous circuits, we had the circuit and we tried to analyze the circuit. We draw the state diagram, state table, timing diagram, and find the output as a function of input. So what is so far the input of the problem was a circuit, and the output of the problem was analyze the circuit and how does the circuit work. But now we want to move like in a reverse direction. Now we want to have some like definition, some problems that we are supposed to design a circuit for those problems. So I'm going to ask you design a voting machine, design a circuit that counts from 1 to 10 and we will learn how to design those circuits. Okay, the first thing we should learn in working and designing the circuit is state assignment. We all know what is state symbol assignment. If you remember about the state symbol assignment, we like assign some symbols for states. So we had, for example, 0, 0, 0, 1, 1, 1, 1, 0, and we say 0, 0 is A, 0, 1 is B, and 1, 1 is C, and 1, 0 is D. This one is uh, state symbol assignment. But what is a state assignment? A state assignment is opposite of state symbol assignment. In a state assignment, we have these symbols and we want to assign some binary variables for those states. Like opposite of a state symbol assignment. So let's see how does it work. State assignment. So a state assignment is the process of adopting a binary coding for the symbolic state of the state table. Okay, so if we have m states, we need to have n bits, and we should find these bits n bits in a way that 2 to the power of n greater equal to m. For example, with 3 bits, we can assign codes to 8 states because 2 to the power of 3 is 8. Okay, so we start from 0, 0, 0 up to 1, 1, 1. So this one is for 3 bits. Using 3 bits, we can assign 8 states. So if we have 5 states, how many bits do we need? We should find n in a way that 2 to the power of n is greater than equal to n. So what is n? Of course, n is equal to 3 because 2 to the power of 3 is greater than equal to 5. Okay, so this one is the like number of bits we need, and this n, in fact, these n's are number of flip-flops, because for each state, each flip-flop can represent 1 bit. Okay, so we should try to find the smallest n in a way that 2 to the power of n is greater than number of states. Any question? Okay, for example, let's assume we have this state table with 2 tables. X is 0, 1, present state, A, B, C, B0, A0, C1, A0, A0, and B0. Okay, so how many states do we have? Any answer? It's easy. How many states do we have here? Okay, so say what was the answer? Two. Yes, one, two, two. It's a very simple question. We have two states. So how many flip-flops do we need for these two states? We should define this n, the smallest n, which is 2 to the power of n is equal greater than 2. What is n? 2. Very good. So n should be equal to 2. So we need 2 flip-flops to build these states. So we need 2 bits. So 0, 0, 0, 1, 1, 0, and 1, 1, because we have 2 states. So we need to assign these symbols to some states. So let's do that. If I assign these symbols to states, I can say A is assigned to 0, 0, B is assigned to 0, 1, and C is assigned to 1, 1. What about 1, 0? We don't care about 1, 0 because we have only 3 states. And now we read about the circuit, the table, okay, x 0, 1, present state. Instead of A, we say 0, 0. Instead of B, we say 0, 1. Instead of C, we say 1, 0. Okay, sorry, 1, 1. And inside the cells, we replace the binary codes instead of the state names. Okay. Okay, so this one is the first part. Any question? Well, what was the last part of the question? I didn't hear the last part. Oh, yeah, yeah. That's a good question. I can put C equal to 1, 0. That's fine. That's okay. We can put it. But there is a like a problem. When we design the circuit, in some points we try to simplify the function using K-map because we might use K-map to simplify the function, and for K-map we know that we should go in this order for the K-map. So let's just keep it in this way. Okay, if there is no simplification involved, yes, that's fine. As you mentioned, yeah, we can go with 0, 0, 0, 1, 1, 0, no problem. But sometimes we need to simplify the circuits. How we simplify the circuit? By K-map. So because we may use the K-map, let's go with this order. So whenever we need the K-map, it's already in order. We don't need to rearrange them again. You got the answer? Yeah. Okay. So we reached to this point, and that's it. So now we have uh, our state assignment. But the other concept I want to teach you before moving to next step of this table is talking about something called excitation table. Excitation table. Let me write it down for you. Excitation table, which is very important. What is excitation table? Up to this point, when considering a flip-flop, we just be concerned with how the response to the various inputs. So when we have a flip-flop, we say, okay, inputs are 0, 1, what is the output? Input is 1, 1, what is the output? So all the time so far, we had the inputs and we tried to find the output, okay? But now we want to learn we want to learn the list of inputs for a given change of the states. What does it mean? It means that I say I have a JK flip-flop, and has two Q bar. I say QT is 0, QT plus 1 is 1. Okay, I have the outputs. Now my question is that what should be the input for this change in the output? So this one is excitation table. It's exactly the opposite of characteristic table. In the characteristic table of a flip-flop, we had the inputs and we determine the outputs. But in excitation table, we have the outputs and we want to find the inputs required for those outputs. Exactly the opposite of the characteristic table of flip-flop. Is it clear? So far we had inputs and we found output with characteristic table, but in excitation table we have outputs, we want to find inputs. Okay, that's very important. Okay, so how we can do that? We easily write the characteristic table, excitation table of flip-flops using the characteristic table. Let me show you. By the way, it's a question. Why do we need to know? Why do we need to know the characteristic excitation table during the design process? When we design a circuit, we usually know the transitions from different states, and we want to design the circuit and design the inputs. So outputs are known. We know the transition in the circuit, and we are supposed to find the inputs. Okay, let's just talk about the transition tables of different flip-flops. Okay, so let's say we have SR flip-flop. SR flip-flop. SR flip-flop has a characteristic table, and has a excitation table. Okay, the characteristic table of SR flip-flop. We already learned it 2 months ago. Q of t plus 1. This is the characteristic table 0, 0, 0, 1, 1, 0, 1, 1. Do you remember what was the output of characteristic table? I will tell the SR flip-flop, but for the JK flip-flop, I will ask you. So you need to help me to write the characteristic tables. For the SR flip-flops, we know that if S is 0, R is 0, Q of t plus 1 is the same as QT. If S is 0, R is 1, the output is 0. If S is 1, R is 0, the output is 1. If both of them are 1, we don't know. Okay, so this one is the characteristic table. But what about the excitation table? Excitation table is the opposite of characteristic table. So we have Q of t and Q of t plus 1, and we want to find S and R. Okay, so 0, 0, 0, 1, 1, 0, and 1, 1. Okay, now under which conditions, if Qt is 0, Qt plus 1 will be 0. If S is 0 and R is 0, sorry, S is 0 and R is 1, or S is 0 and R is 0. So we say if S is 0, and R is D, 0 or 1. Okay, we will have this row of characteristics. So let's discuss a little more. So if S is 0 and D is 0, means no change. What is Q of t? Q q of t is 0, so no change, q of t plus 1 will be 0. This one is the first thing. The second one, if s is 0, r is 1. What does it mean? S is 0, r is 1 means reset. So q of t plus 1 will be equal to 0. Okay, let's just do the second line together. Okay, under which conditions for the input qt is 0 and qt plus 1 will be equal to 1? The first one, if s is 1 and r is 0, which means set. The second one, there is no second one. Okay, so if s is 1 and r is 0, the output will be 1. Okay, the next line. The next line, under which conditions, if q is 1, the q of t plus 1 will be 0. If s is 0 and r is 1, it means reset. Okay, if s is 1 and s is 0 and r is 1, it means reset. The last one is 1 and 1. Under which conditions qt1 will be like remains 1? First thing, if both of them are 0, of course. The second thing, if it's set, s is 1 and the r is 0. So instead of these two lines, we say if it's d and 0. So this one is the excitation table for SR flip-flop. Okay, so let's go and move and try to find the excitation table for JK flip-flop. For JK flip-flop, first let's write the characteristic table. J, K, Q of t plus 1. 0, 0, 0, 1, 1, 0, 1, 1. JK flip-flop 0, 0 means no change. So output is Q of t. 0, 1 means reset. 0, very good. 1, 0 means 1. And 1, 1 means Q part. Very good. Great. Is it Emmanuel? Yeah, good. Very good. Great, Emmanuel. So let's just reverse this table to find the excitation table. Okay, so let's say we have q of t here, q of t plus 1 here, and we want to find j and k. So 0, 0, 0, 1, 1, 0, 1, 1. It says that under which conditions the like q of t, which is 0, will be remains 0. The first thing, if j and k both are 0, or if j is 0 and k is 1, because the output will be reset. So under both of these conditions, the q of t plus 1 is 0. So we say if j is 0 and k is d. If j is 0, k is d. Like next q of t plus 1 will be 0 if q of t is 1. So now let's move to the second row. Second row says under which conditions for which inputs q of t will be changed from 0 to 1. From 0 to 1. Okay, so let's see. First, if j is 1 and k is 0. Okay, if j is 1, k is 0, of course, and the output will be 1. The second one, if j is 1 and k is 0, because, sorry, k is 1, j is 1 and k is 1, because j1, k1 means complement the output. So output was 0, and was changed to 1. So for both 1 and 0 and 1 and 1, the output 0 will be changed to 1. So how we show this? We say it is 1 and D. Okay? So can you think about it for just 2 minutes and tell me what should be uh, like third row? Just think about it. I give you 2 minutes and send me a private chat message. Under which conditions output 1 will be changed to 0? Okay, uh, let me check your answers. Do you hear me, Emmanuel? Hello? Okay, okay, good. So let me check the answers. The answers I do have, it is D1, it is D1, it is D1, it is 01, 0D, 0D, D1, D1, 0D, and D1. Okay, very good. I got 7, 8 answers, and very good. So let's see which one is correct. So let's do it together. The output is 1 and has been changed to 0. The first thing, it's reset. If we reset it, 1 will be changed to 0. So how we can reset it? 0, 1. The second conditions that can change 1 to 0 is complement 1. Complement 1. So how we can complement 1? With 1, 1. Okay? So the correct answer is D1. Okay? So the next line, let me check your answers. Okay, it's D1. Uh, any question? Okay, let's move to the last one. The output is 1 and it changed to 1. Means no change. For which inputs we can have no change? Of course, if it's 0, 0, or one more thing. Can you tell me? Or 1, 0. Very good. If it's set or no change, because it's 0. So for 1, 0 and 0, 0, the output is will be 1. So it is D0. So this one is the excitation table of JK flip-flop. Let's move to the excitation table of next flip-flop, which definitely is easier. The easiest one is D flip-flop. So D flip-flop, it's very easy. So D flip-flop, we have d, and we have q of t plus 1. If t is 0, q of t plus 1 is 0. If t is 1, q of t plus 1 is 1. So that's it. So q of t, q of t plus 1, and it is d. You see that for the d flip-flop, the output is not dependent to the previous state of output, so it only depends to the input. Okay, so whatever we have in the input moves to the output. So if we say 0 0 0 1 1 0 1 1, okay, under which conditions next qt plus 1 is 0? Only and if only d is 0. What about 0 1 if d is 1? What about 1 0 if d is 0? What about 1 1 if d is 1? Just look to q of t plus 1 and copy it in here. So this one is the excitation table for d flip-flop. Okay, wasn't it easy? Very easy. So let's move to the t flip-flop. Any question? So t flip-flop, if input t and we have q of t plus 1, if t is 0, if t is 1, if t is 0, output is q of t, if t is 1, output is q of t bar. So the excitation table, q of t, q of t plus 1, t 0 0 0 1 1 0 1. Okay, so can you just complete this table for me? Tell me what should be I put in the first row. Any idea? Yes, because there is no change. When there is no change, t should be 0. What about the second one? 1 because there is a change. What about the third one? Again 1 because there is a change. What about the last one? Of course, 0 because there is no change. Okay, so this was like about the uh, excitation table of different flip-flops. Okay, we need it. We need this excitation table to solve the problems. Okay, one more thing. Before moving to the next part, one other thing that I should mention. Uh, Let me see. Let's consider this This table. Okay, so the previous example table. So let's just read about the table. Okay. One thing that I missed to mention you, let me just correct it. I think it was missing in my last part. Do you remember when I talked about a state assignment? So we cannot just leave 1 0 empty because we have four possible combinations. So in order to make it complete, so we need to add a new row like this. Because there is no information for that, we say dd over dd over d. So all just don't care. Okay, so we need to have four states because of this binary table, but because there was no data in our table, we just replace all of them with d. Okay, is it clear? So TDD means we don't care what are those values. So let's just copy this table in here. X0, X1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, This one is the table from previous example, and now we want to build a circuit. We want to build the circuit using JK flip-flop to implement this table. Okay, so far if you remember, we learned how to draw the state table from the circuit, but this time we have the state table and we want to design the circuit. Okay, so what we need to do, the first thing we need to do, because it says that we want to design it by JK flip-flop, we need to have the excitation table of JK flip-flop. Q of t, Q of t plus 1, JK 0 0 0 1 1 0 1 1, so it's 0d 1d d1 and d0. The excitation table of JK flip-flop. Okay, now what else we need to do? We need to split this table to two different tables: J1 K1, J2 K2, and Z. Okay, the opposite of we did before. Before we had three tables, individual tables, and then we combine them to build this one. But now we have this table and we want to split it to three tables. Okay, let's do that. We build a new table. X01 00 01 1110, Y1 Y2 Y1 Y2, and this table is for J1 K1. Okay, for the first flip-flop. Let's just complete this table from this table and this excitation table. Okay, let's look one by one. This one is for Y1. Okay, for Y1. Y1 is 0, and it remains 0. Okay, 0, it remains 0. So the JK is 0D. 0. The next part, Y1 is 0 and again remains 0. So we will have 0D. Y1 is 0, change to 1. Look to excitation table. 1D. Next one. We should go over all cells one by one. Y1 is 0 and remains 0. So this 0, which is 0D. Third row, Y1 is 1, changed to 0. D1. D1, yes. D1. The next one, yeah, so just I get happy to see that you answer my like question. So whenever you want, you can just talk. Okay, all of you, like what Emmanuel is doing. So all of you just can unmute your microphone and help me to complete this table. So it is 1 and change to 0. 1 change to 0. It is D1. Last row, it is 1, okay, change to 1 change to D. Okay, because it is 1 change to D, of course we can say it is DD, because 1 change to D, 1 change to D, so it can be D1 or D0. So all of those are correct, so we say DD. And again, the last row, it is 1 and change to D. Okay, 1 change to D, again is D. Yeah, any questions so far? Okay, now we move to the second table, which is for second flip-flop, J2, K2. Y1, Y2, X, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. But this time we're working with Y2 because J2, Y2. Okay, so uh, Y2 is 0 change to 1. 0 change to 1, it is 1D. Very good. The first row, second column, 0 to 0. 0 to 0, 0D. Second row, first column, 1 to 1. D0. Very good. D0. Second row, second column, 1 to 0. 1 to 0. No, no, D1. Okay, D1. Third row, first column, 1 to 0. 1 to 0 is D1. D1. Second row, third row, second column, 1 to 1. D0, very good. Last row, first column, 0 to D. It is DD. And last column, 0 to D, again is DD. Okay, so we completed the second table. Any question for this part? Okay, now one more table for Z. Okay, for Z, again we say X, Y1, Y2, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. We just simply copy paste. There is no excitation for the output. Output is just those values in like in this table. So we just copy those values. So it is 0, 0, 1, 0, 0, 0, D, D. Okay. Now we reach to this point. Now I want to answer the question that was asked by Emmanuel, that do we have to go with the order of 0, 0, 0, 0, 0, 0, 1, 1, 1, and 1, 0? And I said sometimes we need to simplify the circuits by K-map. Exactly, here is the answer. For Z, we want to find the function based on this table, Okay, so these are these. So simple as possible group that we can find is just a single group of 1. So if you remember K-map, so Z will be equal to X bar, Y1 bar, Y2. This one is K-map. This one is like output. Okay, this one is the output. What about the other two tables? Okay, so the other two tables, because it's JK, we need to find J separately, K separately. What we can do, we again can split this table to two tables. So one here for K1. So x y1 y2 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0 0 1. What I can do, just I fill this table with the information I have. So from this table we know that the first variables are j's. So we say 0 0 1 0 d d d d. This one is j. What about k? Is d d d d 1 1 d d. Okay, we just split this table to two individual tables, and now we need to write the equations. So let's just consider this table as a K map. This table. So we need to like find a function. Which cells should we group? So if we look to this one, there is no point to grouping these together because there are D, and the best. Say it again. No, I want to group ones. One, not zero. Yeah, I want to group one. Just this one, these two. Are we agree? Because it's like the best option we have. We cannot have four together because so this one is the best option we have, which is in the form of power of two. If this one was also D, yes, we could group these four together, but it's not D, so it's zero. So the best option is 1D. So if we group 1D, the function is x bar y2. This one is the function of j1. Any question? Now I'm sure that you can tell me what is k1. At least one of you or two of you, I'm sure that know the answer. y1 y2. Can be simplified more. That is correct, but it's not the best answer. The best answer is, let's consider all of these one, and let's just group all of them together. So k1 is equal to 1 because they all are these and ones. So we can. Yeah, I got a question here on the that it says, will this lecture be on Sakai later? Of course, yes. It will. I hope that it's recording because I'm using two different applications to record it. But it's very useful for you to listen here, ask your questions, participate in the discussions, and I also will upload it on Sakai by tonight if it's recorded. That I think it is. So, so K is one. So let's move to the second table, the second one, and try to simplify, not simplify, to solve this J to K2. So for J to K2, again, we need to have two tables, like this, like this, and we just insert the values. Okay, now we reach to this point and we want to find J2 and K2. So J2, let's see what we can do. The group of how many? Yes, this one. This one is the best option. This one is the best option, of course. So what is the like equation? Of course, it is equal to x bar. X bar. Okay. The next one, k2. So you see, we just finding the equations j1, k1, j2, z, and now we are going to find k2. Okay. So let's find k2. So let's look here. So how we can. So this one cannot be grouped with this one. So the best thing is a group of two here and group of, yeah, two here. So this one is the best way we can just simplify this function. And this one is x bar, y1 bar, y1, sorry, x bar y1, yes, plus uh, x y1 bar, which is equal to x all y1. Okay, so x all. Now we got all the equations, for jk flip flop. So we have j1 is equal to x y2, k1 is equal to 1, j2 is equal to x bar, k2 is equal to x all y1, and z is equal to x bar y1 bar y2. Okay, now that we reached to this point, it's time to design the circuit. So for the designing the circuit, how many flip-flops we need? Of course, two flip-flops. So one flip-flop, two flip-flops, j1, k1, j2, k2, q, q bar, q, q bar, y1, y1 bar, y2, y2 bar. Okay, so this one is like a 2jk flip-flop. What about, and we have input x. We have input x. What is, and this input x also we complement it because we need x bar as well. So what is j1? J1 is x bar y2. So we get y2 and x bar, and this one is j1. What about k1? K1 is connected to VCC because it's equal to 1. What about J2? J2 is X bar. J2 is X bar. What about K2? K2 is X all of two signals. Signal X, and signal Y1. Signal Y1. What about Z? Z is X bar, Y1 bar, and Y2. And this one is, and we designed the circuit. Okay, so we designed the circuit. By the way, don't forget the clock. This one is also closed. So you see, we designed the circuit by having the state table. What is our original data? This one is the output of our problem, but the input of the problem was, what was the input of the problem? This one. This one was the input of the problem. We had it in the state table, and we designed the circuit that implements this state table. Okay, any question? Okay, by the way, sometimes we might want to see the output every time the clock is active. So we might need to see the output anytime which the clock is active. It depends to the design. If it's the case, if it's the case, we can just connect the clock cycle to the output as well. So anytime that the clock is active, we see the output. Okay, so it's based on the design. Questions? No question? Okay, so let me write down these steps for you for your reference, and so you can use these steps for your other problems that we will solve. So design algorithm. To design um, not to design, sorry, the design of the synchronous sequential machine can be summarized by the following steps. Step 1, from the word description, from the word description and the specification of the desired operation, derive derive the state diagram, the state diagram for the circuit. So deriving the state diagram is the first step of this design algorithm. Can you hear me? This one is step one. So like deriving the state diagram. So first thing we do, we derive the state diagram. Step two. Step two. Obtain state table from state diagram. This is the step two. Step three. Reduce the number of states if possible. How we can reduce the number of states? Do you remember? By inspection or partitioning. Step 4, Step 4, assign binary values to the states, the same state assignment that we discussed at the beginning of the class. Assign binary values to the states, which we call it state assignment. Step 5, determine the type of flip-flops we need. Okay, what type of flip-flop we want to design the circuit? Are we going to design the circuit with D flip-flop, T flip-flop, JK flip-flop, SR flip-flop? So determine. This one is usually given in the problem. In the problem it says design the circuit with this type of flip-flops. Determine the type of flip-flops to be used and obtain the corresponding excitation maps or excitation tables. The next step is step 6. Determine the output and flip-flop equations that we did. The main part is this step 6. And final step 7, draw the logic circuit. Okay, this is the 7 steps that we use to design a circuit. Okay, sometimes we start from step 1, but sometimes we start from step 2. Sometimes we have more descriptions and we are supposed to find the state diagram and then obtain the state table. Sometimes the state tables are given and we just need to move from step 2 forward to step 3, 4, 5, 6, and 7. Any question? Okay, so I have one example. Example. Design asynchronous sequential circuit to implement the following state table by A. T flip-flop, B. J. K flip-flop, and C. T flip-flop. Okay, so I'm going to solve this part A, okay, and part B and part C is your homework. I will open an assignment section, so you have until the next Tuesday at 12 p.m. to 12 p.m. in the noon, not midnight. Next Tuesday noon to submit your assignments. So I will do part A, and you do part B and part C, and submit it on Sakai by the next week. Okay, so part B, part B and C are homework. Okay, do next Tuesday. Do next Tuesday. Okay, guys, wait a second. The cell phone, mommy cell phone. Okay, okay, give it to me. Let me tell you. Okay, sorry. Uh, Sometimes my kid, she wants to play with me. So okay, and so part B and C uh, our homework. So let's go ahead and solve part A together. So first thing we need to have is the table. The table is here. The table is here. So this one is the table. Don't forget to submit the homework, okay? A, B, C, D, A, 0, B, 0, A, 0, C, 1, B, 0, D, 0, C, 1, D, D0. Okay, so this one is the table we have, and for part A, we want to implement the circuit by T flip-flop. The first thing we need to do is try to reduce the states, because part A already was not part of this problem. Part B, we have a state table, and the state table says reduce the number of states if possible. Okay, so how we can do that? By partitioning. First, by inspection, nothing is here. So by partitioning, we try to reduce the number of states. Let's do that together. And P0, A, B, C, D, X is 0, X is 1. The outputs 0, 0. I hope that you remember the partitioning. B is 0, 1, C is 0, 0, D is 1, 0. And we go to P1. We select those that are have the same output. So we say A and C, B and D. A and C have the same outputs. B and D each has like different output. So now for x0, x1, we need to write the next state. For A, if x is 0, 1, A is A, B. For C is states. So A, C, C, D are single. So of course they are in the same same partition, same block. What about A and B? A and B are not in the same block. What about B and D? B and D also are not in a single block. So we need to add another partition. So P2, which we have A, C, B, D, x is equal to 0, x is equal to 1, A, B, B, D, A, C, C, D. All of them are, of course, single states, so they are not in different states. So P3, A, C, B, D is same as P2, so P3 is equal to P2. So the function is A, C, B, D. It means that this function is irreducible. So it's not possible to reduce this function. Reducible. Okay, it is irreducible, so we cannot just reduce this function. So we need to keep it as is in equation. So now that we got to this point, let's go for state assignments. So for state assignments, so let me just put some notes for you. So this one is step 2, step 2, and this simplification is step 3, step 3, and now we need to move to step 4, which is state assignment. For state assignment, we say A will be 0, 0, B will be 0, 1, C is 1, 1, and D is 1, 0, and the table will be equal to this table. So it's X, not present state, Y1, Y2, Y1, Y2, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. I just try to like bring the states from this table. Okay, guys, let me just make sure that mine is yeah. I try to get the states from this table using these assignments. Fill this table. Okay, so if we do that, we will have 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, and 1, 0, 1. Okay, so we reach to this point. In the next step, we need to like have the step 5. We need to have our excitation table. So because we implementing with is it the step 5 or the step let me look at the steps. Step track of okay, yes, step 5. Step 5, we need to have the excitation table for T flip-flop, Q of T, Q of T plus 1, it is a T, it's a 0, 0, 0, 1, 1, 0, 1, 1, so it's 0, 1, 1, 0, so this one is the excitation table for T flip-flop. Now what we need to do, we need to split these to two tables, in fact two tables, one for T1, the other one for T2, and the third one for output. So for T1, we draw the circuit, draw the table like this. So it's X, Y1, Y2, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, and we use this table to solve it. So the present state is 0, change to 0, 0, 0, T is 0. Okay, exactly. So we use excitation table to complete it. So it is 0. The next one, 0 changed again to 0, the same thing, again it's 0. The second row, first column, 0, 0, again is 0. The second row, second column, second row, second column, 0 has been changed to 1, so it's 1. Third row, first column, 1 changed to 0, so T should be 1. Third row, second column, 1 is changes to 1, so 1, 1 is no change, in fact 0. The last row, first column, 1, 1 is 0, and 1, 1, 1 again is 0. Okay, so we reach to this point. This we repeat, so this one is T1 for T1. The same thing for T2. The same thing for T2. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So the same thing for T2. So for T2, this time let me just erase this. We should look to Y2 and Y2 inside the table. So 0 to 0 means no change. No change means T is 0. Yes, this next one, the next one, 0 change to 1. 0 change to 1 means change. The output should be, the T should be 1. If we complete this table, we will have 0, 1, 1, 0, 0, 1, 1, 0. Okay, the last table, it's the output. Okay, this one is the output. So it's X, Y1, Y2, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. We just copy paste this output from this table and put in the new table. So we will have 0, 0, 0, 1, 0, 0, 1, 0. So this one is Z. Okay, so we reach to this point because this type JK flip-flop inside each cell we have only one variable. We don't need to re-split these tables. If you remember in our previous example, when we reached to this point, we had something like 1D, 0D, D1, and we had to again re-split it to two other tables. But here, because it's only one variable, we don't need to do that, and we can simply find the equation. So, can you tell me, is there any way to simplify this K-map? Of course, there is not, because we have 1, 1 here and 1, 1 here. Yeah, so and they are not connected. We don't have on don't care variables. So we can simply we need to put like all variables. So we need to say t1 is equal to x y1 y2. It's not x bar, sorry, x bar y1 y2 plus x y1 bar y2. So this one is for this part. In order to implement this one also, we can say, okay, this one is equal to, let's factor out from y2. If we factor out from y2, we will have y2 x x or y1. It's easier to implement. Okay, so for the second table, we have four ones. Is there any way to group them or no? Yes or no, Emmanuel? Or any other response? Can I group these ones together? Of course, if we look to adjacent cells, none of them are adjacent. So yeah, this one is alone, this one is alone, this one is alone, and this one is alone. We cannot group them together, okay? So T2 is equal to the worst case scenario. We have four ones and no way to combine them, okay? This one is the worst possible K-map combination. There is absolutely no way to simplify it. So we need to say x bar y1 bar y2 plus x y1 bar y2 bar plus x x y1 y2 plus x bar y1 y2 bar. This one is the table. We can just factor out we can factor out x from two of them and say it's y1 x or y2 x no, in fact, plus x bar y1 x or y2. I simplified these four in this form. Okay, so this one is the second. This one is the like T2. What about Z? Also the same problem for Z. There is absolutely no way to combine these ones together. So Z is x y1 bar y2 plus x bar y1 y2 bar. Okay, so we have these four four like equations, and we need to implement the circuit. Okay, if we implement the circuit, we need to have two flip-flops, T, T1, T2, Q, Q bar, Y1, Y1 bar, Y2, Y2 bar. Okay, and we have X here. Let's go start from Y from T1. From T1, T1 is Y2, X, and Y1 should be X or. So X is here, X is here, and Y. I'm just looking to here. I'm just trying to build this part. Okay, so X and Y1. So I get Y1, X and Y1, X all together. This one and with Y2 and with Y2 is connected to T1. So this one is T1 connection. What about T2 connection? T2 connection, we should XOR y1, y2, and x null. So we have an x all, and of course if it's not x all it gives x null. So these inputs should be y1, y2. So let's see, y1 is coming from here, y2 is coming from here, this one is y1, y2. Okay, so this one is x all, which is and by let me just go the other way, and by x bar. Okay, this one is 1. The second part we get x where is x? X is here. No, not here. We get x, and these two are all together. Okay, it's a little complicated, but this one is the final circuit for T1 and T2. What about Z? Z is here, which is all of two signals. Those two signals, let's look to Z, X, Y1, Y2. So I get X from here. Okay, X, Y1 bar, Y2. This one is one signal. The other signal is X bar, X bar, Y1, Y2 bar. These two goes to OR gate, and this one is the C. This one is the the whole entire circuit. So this circuit is the circuit that we need to build to implement that table, state table, and I want you to repeat the same thing for JK flip-flop and JK flip-flop and D flip-flop. So you need to complete these steps. You need to complete these steps and find the equations. And when you got the equations, after that you need to, after finding the equations, you need to divide the circuit. Any question? Okay, I will post this lecture and my voice from the previous lecture, because as I said, the previous lecture video was not recorded. I will post them on Sakai. I will open an assignment. You have until the next Tuesday 12 p.m. noon to submit the assignment, and see you next week regarding your quiz. Exam 2, I will send you a notification announcement to and let you know whenever, as soon as the grades get available on Sakai. Any question? Okay, have a great day. See you next week. Goodbye. You're welcome.